Okay, so this is going to be for experiment 1, and we're going to be talking today about uncertainty in significant figures. Now, for experiment 1, we need it's all about scientific measurements. So it's about how we take measurements. And so we're going to use a variety of tools, but we're going to talk a little bit about how we can tell the importance of those values that we write down. So all measurements have some amount of uncertainty. The question is just to what degree, right? So when you measure something, we have those two types of numbers. We have exact numbers, which means that there's no uncertainty with them. It means we're certain of that whole amount. So when we count the number of eggs inside of a carton, we know that there are 12 eggs in there. There's no uncertainty about that. When you use 2 of them, you know that there's 10 eggs in there, right? That's an exact number. But anytime we use a tool to make a measurement, then there's going to be some uncertainty in it. So let's look at the population of the Earth, right? There's 7.442 billion people on Earth. And let's say that your cousin has a kid tomorrow. Do we want to update that to now say that there's 7.422 billion and 1 people on Earth? Does that make sense that because we know 1 more person is born, that we should then report out that value to add in that 1 more person? So when we think about that, when we were measuring the amount of people, there's some amount of uncertainty in there. Do we really know that there was all the way down to the single people, how many people there were? Or does that value change? Is there some uncertainty in there? And so when we look at our number, the uncertainty of a given one, we want to make sure that when we express those terms or our measurements, that we express that same concept to whoever we're sharing this with. And so that's what we're looking to do. Now, what we're going to do next is we're going to take this measurement here. We have 2 rulers and we're measuring the length of a baby carrot here. And we want to write down what values we think we see. Now, normally we would do this in person. You guys would be able to do this in groups of 4 and we could compare. But in the meantime, what I want you to do is look at ruler A, and I want you to write down that measurement. How long do you think that carrot is? And then look over at ruler B and do the same thing. What is that length? Is it 3 centimeters? Is it 3.1 centimeters? Is it 4 centimeters? Is it 4.5 centimeters? Whatever you think it is. Maybe it's even farther than 4.5. Maybe it's 4.52, right? Whatever value you think it is, go ahead and write that down. So what we want to think about is when we're expressing them, is we want to make sure we're giving as much information as possible. And we don't want to be leaving anything out, but we also want to still show the information that is provided by that ruler. So let's look at ruler B for a second here. Using our ruler, we can see that it's clearly past 3 centimeters. So we can write that down as 3. But we could give some more information there. We don't want to say that we're uncertain about that 3. We actually know that it is that 3. So we know that it should be 3 point something. And so in this case, I might say that it's 3.2 centimeters. A little bit past that. For ruler A, I can kind of see that, well, we're definitely that 3 centimeters. And we can see that its length lies somewhere between that first line and that second line. So I know that that has to be at least 3.1, but less than 3.2. And so I think that it's kind of close to the middle, maybe a little bit past the middle. So I'm going to say that that is a 3.17 centimeters, about 3/4 of the way there. So when we're expressing our values, what we want to do is we want to write down that term. So we have our certain numbers. For ruler A, that's the 3.1. We know that those values are true. We know that they can't be 3.0. We know it can't be 3.2. And on ruler B, we know that that one has to be 3. These ones are our certain, right? There's no uncertainty about them. Those are definitely there because we can see them from the ruler. Whereas that 7 and that 2, this is where our uncertainty starts. It's where we had to make an educated guess. And that's what we want to do when we make our measurements, is we want to use our tool to its full potential. So we shouldn't just stop at the 3.1 centimeters for ruler A, and we shouldn't just stop at the 3 centimeters for ruler B. We should always go 1 digit past the lowest marking. So this is a plus or minus 1 milliliter, or sorry, not milliliter, 1 centimeter. And so we should be going 1 past that because each of those marks is the 1 centimeter. Ruler A is 0.1 centimeter marks, and that's why we should go 1 digit past that. That's why we go to the 100. Now for our uncertainty inside of our rules, the idea is that we're going to take that value that we see, and that last digit is going to be where our uncertainty is. So when we report something as 8 inches, we're really saying that that is 8 inches, and then there's some uncertainty in the 8. When we look at 138 moles, then it's saying that we know the 130 part, but the 8 in there has a little bit of questionable parts. So ruler A, we are certain to that 0.1 range, but our uncertainty is that in that 0.01 centimeter range, so where the 7 is. And so when we're recording those down, then that's what we want to be including. So if the number is counted, then we can consider it to be exact, and it has as many significant figures as you need. So 3 steps or 2 coins or 6 people, right? If you're counting something. But anytime you're using measurements, if it's not going to be exact, not something that you count, then there's going to be uncertainty, and we're going to assume that it shows up in the last one. So significant figures is our way of talking about numbers that matter. So sometimes when we're performing calculations or writing down numbers, we're going to get some digits that exist beyond the accuracy of that measurement that we can make, or the precision of that measurement that we've made. And those digits we can then get rid of. So the ones that we remain are called our significant figures, or sig figs for short. And they're the ones that we have confidence in and where we have our educated guess. So in this case down here, we're trying to express them with some amount of uncertainty. So the uncertainty is what comes after that plus or minus sign. So in this case, we have 6.845, and we know that the uncertainty lies somewhere in that 0.1. So we want to rewrite that number to show that that 6 we are confident in, but on that 0.8, we're not sure. So that should become 6.8, where we know that the certainty of the 6, but the uncertainty of that 0.8. Let's look at this next one, 8.3982. Its uncertainty is coming in the 4th digit after the decimal place, so 8.3982. And so we don't need to do anything to that number. We can leave that as it is, 8.3982, because its uncertainty is being expressed correctly. Looking at 7.90873, if our uncertainty is in the ones place, then all of this over here is going to get dropped. Now, when you're making that choice about how to drop something, we have to think about whether we need to round it in order to accurately show where our value should be. So we could just take out the 0.90873. We could just write this number as 7. But that's not actually what it's closest to with our plus or minus 1. So we want to look 1 past the digit that we're going to keep. So we're looking at the first digit that we're getting rid of, so in this case the 9. And if it is a 5 or higher, we're going to go ahead and round that up. So our 7.90873, we should round that up to 8. When we look back at our first one, 6.845, you can see that that number that we were getting rid of was our 4. And so we didn't have to round that up because it wasn't a 5 or higher. So that's why it became just 6.8. And so you want to take that into account as you do these other ones. So 40.980, that remains the same. This one is 40.980. This one we should go to the 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. So we're looking at that 8. The 2 is lower than a 5, so we can go ahead and just drop that off. And we have our values. And so that's how we can use our uncertainty to write those down. Now the tricky part will be this one. And so I'm going to let you think about that. We're going to actually talk about this a little bit later when we think about our scientific notation. So think about how you would write that. How could you express that where we would show that that 0 is important and the 0 is not. And so when things aren't zeros, then it's pretty easy to tell. But significant figures become complicated with our zeros. And so this is where we have to think about our significant figure rules. So zeros are complicated because sometimes they are there just to hold the place in order to show that it should be a big number or show that it should be a small number. And it's there because we can't write it in normal notation without that 0. But there's no certainty of that 0. It's just there holding that place. And so when we think about this, we're really thinking about several different types of zeros. The first ones, we're going to call them leading zeros. So leading zeros are all of the ones that come in front of the first non-zero number. So like these. All 4 of those, whether they're beyond the decimal point or below the or after the decimal point, those are all leading zeros because they all show up before the 5. So all of them are placeholders. The nice part about leading zeros is that they are never significant. They're always considered to be non-significant. On the other hand, zeros that happen after the first non-zero digits are not leading. So they can exist in kind of 2 types. One of them is what we're going to call as being trapped. These are ones that are stuck between, oh, that is the wrong color for that one. They're stuck between 2 non-zero numbers. So we call them trapped because they're stuck. Now, the nice part about non-zero numbers that are trapped is that they are always significant. So those 2 zeros between the 4 and the 9 are going to always be significant. But those leading ones in front of the 4, those are never significant. The last type that remains are what we call trailing zeros. Now, trailing zeros, they come after the decimal point, or sorry, trailing zeros come after the last non-zero digit. And the tricky part is that they are sometimes significant and sometimes they aren't. So trailing zeros come at the end. So that's looking at these 2 zeros over here. And how we know whether they're significant or not is we're looking for a decimal point. If there's a decimal point anywhere in that number, they are going to become significant. If there's no decimal point, then they're not going to be significant. So let's do a little practice with this. For each of these, we want to think about which ones are significant and which ones aren't. So these 3 zeros here, we would consider those trapped because they're coming between 2 non-zero numbers. And so if we wanted to list the total number of significant figures, this should be 6. On this second one, we have 2 types of zeros. We have the 2 trapped ones here, but we also have one more at the end, a trailing 0. So we know the trapped ones are going to be significant. And in this case, we know our trailing 0 is also significant because there is a decimal point inside this number. So we can count all of those, 1, 2, 3, 4, 5, 6, 7, 8, and we have 8 significant figures. This next one, we're looking at the 3 trailing zeros again, but there's no decimal point there. So those 3 are not considered significant. And so we only have 3 sig figs for that one. Whereas our next one, you can see that while it's trailing zeros again, there is a decimal point. And so we do have 6. So those 2 examples are there to show you how important those decimal points are and why you have to include them, or why sometimes numbers are written that way. Sometimes they have that decimal point there because it just so happens that both the hundreds, the tens, and the ones digits are 0 in value, not that we're not sure of what their values are. During this next one, we have our leading zeros, and those are never significant. We have our trapped, or we have our trailing zeros down here at the end. And those are going to be significant because there is a decimal point in this one. And so we should have 1, 2, 3, 4, 5, 6 significant figures. Looking at our next one, we have those leading zeros again. Never significant. We have our trapped 0 right over here. Those are always significant. And the trapped 0 here, always significant as well. So we have a whopping 9 significant figures in that one. This one here, we have trapped again, we have trapped again, and then we have some trailing. Now in this case, those trailing ones are not going to be significant because there's no decimal point. And we should have 1, 2, 3, 4, 5, 6, 7, 8 significant figures. And so that's our significant figures. Now, sometimes it can be tricky for us to write numbers in normal notation. Sometimes when numbers are really big or really small, there's all of these extra zeros that we have to include there. And so what we can do is we can do something called scientific notation. Now, the nice part about scientific notation is that all numbers that you're writing in scientific notation, all digits shown, are going to count as being significant. The tricky part is making sure that you are writing them and expressing them in the correct way. So scientific notation means that you are going to have some number a, and it's going to be expanded to the power of 10 to the x. So what that looks like is if you were having 310, you could think of 310 as kind of being 3.1 times 100. That would get us 310. And 100 is really the same as us as saying 10 to the second power. So it's a way for us to include those 0 placeholders without having to include them in our base number. Now, proper scientific notation, the value of a has to be greater than 1, greater than or equal to 1. So it can be 1 exactly, but it can't be 0.999. That won't work. And then it has to be less than 10. So that means that 0.9 would not be correct, but 9.99 is totally fine. So when you're looking at your scale, you have to use your exponent x in order to get it into the right range. Now, positive values of your exponent are going to give you bigger numbers than 1. So it's going to start at 10 to the 1, which is times 10, 10 to the 2 times 100. Whereas smaller numbers, smaller exponents, is how we get less than 1. So 0.1, 0.01. And so that's how we adjust them. All of those digits that are shown in a scientific notation number count as significant. So when we look at it, 10,000 as written on the left, we would write that as 1 times 10 to the 4. Whereas 10,000, with that decimal point there, we would include that as 1.0000 times 10 to the 4 in order to show that there are those 5 significant figures and that all of those zeros are significant. So here's some practice ones for that. We have 46,800, and so we can write those out in scientific notation. So go ahead and pause this video, take a moment, write those out, And then we're going to go ahead and write the answers. So this should be 4.68 times 10 to the 4, 9.032 times 10 to the minus 3. This one, all of these zeros aren't going to be significant, so we don't need to include them. 3.79 times, and then we should be to the 10 to the 7th power. Now, while these aren't significant, these two are, so we want to make sure that we include those. So that should be 7.32400 times 10 to the minus 9 in order to show that correctly. We should also feel comfortable going the other way. So going from them being in normal notation to standard notation. And so this one is going to be our 1.34 times 10 to the 6. And so go ahead and pause your video, take a moment, solve these 4 examples. So we should have this as 1,340, or 1,340,000, right? It's got 6 zeros after that. This one should be smaller than 1, so 1.123323. 3.0 times 10 to the 8, 0.123456730. We should definitely have that extra 0 at the end. 2.00 times 10 to the 6. Now this one is tricky because it would look like this, and this is the problem with standard notation, is sometimes it can't accurately express this value. There's no way for me to show you that just these 2 zeros are significant and these other ones are not. If I put a decimal point here, making my trailing zero significant, it makes all 6 of those zeros significant. If I don't put it, it makes all 6 of them not significant. And so that's why in this example, we wouldn't write this in standard notation. We would just want to leave it in its significant figure, or in its scientific notation, in order to correctly represent that number. So for this class, we can use scientific notation, we can use standard notation. There will be times where I might ask you for one in particular. So like for quiz number 1, I might ask you to write it in scientific notation, or I might ask you to write it in standard notation. But there are times where you won't be forced to use scientific notation, because just like example number 4, there might be a number where you just can't write it in standard notation and still express it correctly. The last part of our significant figures is our rules. And so there's kind of 2 rules for our significant figures. The first one has to deal with multiplying and dividing. So multiplying and dividing, when we do that, when we go through that mathematical operation, our answer is going to be equal to the same number of significant figures as our measurement that had the lowest. So in this example, we have 893 times 12, and that would give us 10,716. However, in order for us to show the significant figures correctly, we would look at this. 893 has 3 sig figs, 12 has 2, and so our answer should only have 2 sig figs. So I look at this 7 here, the first one that I'm going to remove. It's more than 5, so I have to round it up, and that's how we get 11,000. Don't just drop off that value. You do have to do the correct rounding. Same thing for this next example. 3.098 has 4 sig figs, 6 has 1, and so our answer should only have 1 significant figure, which is how we got to 40. Now, remember that if you have an exact number, then that one has as many significant figures as you possibly can need. And so if we have the average number of steps reported by 13 people, we don't want to be held down by that 13. That 13 is an exact number. We know that there were 13 measurements that got brought in. That doesn't hold us down. So our answer, instead of having only 2 significant figures, should have 5, which is how we got that 160,020. Let's go ahead and practice that. You can include your units as well if you feel comfortable with that. So on our first one, we should have 3 sig figs times 3 sig figs, so our answer is 3. Second one, we have 4 sig figs times 2 sig figs, so we should have 2. Our third one, remember these trailing zeros are not going to be significant because they come, they don't have a decimal point. And so they are going to be 2 sig figs times 4, and so our answer should be 2. Now you might have wanted to write it as 1 million here, but that would not be correct because it doesn't have 2 sig figs, it only's got 1. So we have to use our scientific notation in order to get that correct. Our last one, we have 5 sig figs times 3, and so our answer should also be 3. Very good. Rule number 2 is for our addition and our subtraction. Now, addition and subtraction follows its own set of rules. So when you do addition and subtraction, it doesn't matter how many sig figs there are, it all depends on where they are. So to visualize this, what you do is you basically line up your adding or your subtracting values. Now, what that means is the answer can only have as many digits, or can only have it to the place where our uncertainty begins. So what that means is if we add 3.00 centimeters and we subtract from that negative 0.045 centimeters, 3.00 goes all the way to the hundreds, 0.045 goes to the thousands. So when we take our answer is only going to be able to go to the hundredths because that's as far as our 3.00 went. So it's kind of like it matches our shortest number. Now, sometimes that gets a little bit confusing because you might have a lot of numbers before the decimal point, but basically you're just trying to line them up, and whichever one is furthest to the left, that's where you're going to stop. So in this 16.320 minus 2.98, we go to the thousandths in the top one, the hundredths in the second, and so our answer should only go to the hundredths. This works for both addition and subtraction. For some reason, I just happened to write all subtraction problems. But let's say that we had 3,100, and we add to that 312. That would become 3,412. But our answer, because these are not significant, would be tied in with 3,400. Because our first value is tied in the hundredths place. That's where its uncertainty began. So go ahead and take a stab at these. You can go ahead and pause this video, make your efforts, and then we're going to put up the answers so you can check. Make sure that you match those values up. And there is one mistake. This example number 5, it should be 120 with a decimal point. So I'm going to go ahead and add in that decimal point right there, because that 0 is significant. So we want to make sure that we have that there as well. Very good. Now, when you get a problem like this, where you have kind of a bunch of different things going on, the important part to remember is anytime you change rules, do your rounding. So when you go from addition, like we do a plus b, when you then finish that, then you need to do your sig fig rules. When you then multiply times c, then you need to do that sig fig rule, because then you're going to do subtracting d. So every time you swap back and forth, you have to change that rule and do that rounding. But if it was just a times b times c times d, you can do all of that math together and just do your rounding at the end. So you just have to look at whether or not you're changing rules or not. So if you change the rules, do the rounding. All right. The last part for our lab that we're going to talk about is going to be on reporting error. So we talked about uncertainty values. Those are those plus and minus ones. Now, those are there to kind of show the error that we get from either our measurement in terms of the tool or from our technique. And it's actually quite involved in how you come up with those plus or minus values. So we're not going to use that primarily in our class. We're not going to do what we call error propagation, because you would have to kind of look at your tool, how you took that measurement, what math you did with that measurement, and that's how you pass that error bar along throughout your process. And it's kind of an involved process. We're not going to do that for our class, but we do want to understand how to change things. So those plus or minus values, they're associated with that error or that uncertainty in those measurements. So we want to use those general rules of thumb that we've been talking about, where we're going to have our number and the last digit's going to be where our uncertainty lies. And so we're going to have to adjust our values to help show the correct uncertainty. So as an example, 3.03 has this written as a plus or minus 0.05. What that means is that that 0.05 is giving us a lot of uncertainty there, where that 0.03 would be. It's so much uncertainty that we don't have any confidence now in that 3. So we're going to round that up, and we're going to report that number as 3.0 instead of as 3.03. That takes care of that plus or minus 0.05. So any value 5 and up, we should round to the error in front of it. If it's less than 5, then we can round down. So 3.03, we can report that as 3.03. Or sorry, if it's 3.03 plus or minus 0.03, we can report that as 3.03. Whereas 3.03 plus or minus 0.05 has to get reported as 3.0. As we're going through this, just make sure that on your exams, your quizzes, your lab reports, you're never writing your own plus or minus values, right? We're not doing that correct error propagation, and so you want to make sure that that's not how you're expressing them. If you drop off a value at the end of your measurement because of that error, so like when we dropped off this 3, make sure you follow the rounding rules, so that way we're correctly expressing it. So looking at these, we have 12.3 plus or minus 10. Our uncertainty is going to be in that tens place, so that's going to be with that 1. And so we can look at that 2. We can consider whether we keep it or drop it. We're going to drop it because it is past the uncertainty of our error. And because the value is a 2 instead of a 5, then we can just go ahead and bring it down. Go ahead and make an attempt for your next ones, and then we'll put up the answers. So for our next ones, you can kind of see that we should have that as 1300. So that way our 100s minus line up. 0.0489. We should line that up with 0.049. And that's because our uncertainty is starting to get there. Actually, now that I look at that, 0.0489, this should be in the 3rd digit, and so we should be able to keep it all the way to that 9. So this one isn't correct. There's a mistake there. It should be 0.0489. And that's because that 0.004 is less than our 5, so we can round it out. On this next one, where it's the 0.005, then we need to take that into account. And so this should become 0.048. And since we can't keep that 9 here because of that 5's uncertainty, we have to look at it. That 9 is going to round us up, and we're going to report that as 0.049. Looking at this next one, we have 1, 2, 3, 4. So we start 3 after decimal point. 1, 2, 3, 4. And so we want to look at where that value begins. So we're looking at that beginning of that 1. That's 1, 2, 3, 4, 5, 6, 7 after the decimal point. So we go 1, 2, 3, 4, 5, 6, 7 after the decimal point, and that's why we had to add that 0 in to correctly show where our uncertainty began. This one's 1, 2, 3, 4, 5 after the decimal. So 1, 2, 3, 4, 5 after decimal, we can leave it as it is. So I hope that helps. That should get you guys through the first part of your significant figures. If you have any questions, make sure to ask. Otherwise, good luck.